Hello everyone. Today I'll be, giving a tour of my newest open source project, which is called Nature2D. And so I created this like 3 months ago, back in October of 2021, and I'm still pretty actively maintaining it. So yeah, I'll be explaining what this library is, and all the features that come with it, and what made me make this library in the first place. We'll also be looking under the hood to see how everything works and how physics objects function, as well as how I handle collision detection and response. And at the end, I'll show you a code example of how easy it is to create your own simulations. And so let's start with what the library is. So let me just open this up. Yeah, just a second. All right, so what the library is. So it's basically a physics library, or to be more specific, it's a physics engine made in Roblox and for Roblox. But this is different from any other physics engine and the inbuilt physics engine of Roblox. And so it's a 3D physics engine. It makes a use of two-dimensional elements like frames, pixels, and tables. So you can basically convert your UI into physical components on the screen. And so this is made to be specifically created for simulations, games, or anything else that requires physics, but in 2 dimensions. And so it comes with a lot of features, and some key features are it has rigid and soft bodies, it has constraints, it has smooth rigid body collisions, back to pretty much optimized, and it comes with time and speed scaling, so you can control how fast or how slow your speed and the speed of the simulation goes. And it comes with collision filtering, and it's packed with a lot of customizations and configurations you can mess with. So you can edit, friction, the gravity, or the masses of the different rigid bodies, and a lot more that comes with it. And so what made me create this library? Well, initially it was for fun. I didn't have any intention going forward with it. I used to showcase my creations that I made with this library on the developer forum, and I used to get a lot of feedback, which made me ultimately release this out to the public. And key was to go
Sorry to interrupt, Jai. There's a bit of a connection issue, I think. It's been getting better or worse. Like sometimes your voice is a bit uh mangled. Is everyone else experiencing the same
Yeah, he's coming across as a robot right now.
a different network. Um, yeah,
Jai, can you say something? Yeah. Maybe if there's any way to reduce your video stream quality, that might be a necessary compromise.
All right, is it better now?
Yeah, that's good.
Yeah, it's great at this moment. I'll let you know.
Where was I lost for you? So where was I?
Uh, It was happening like intermittently, but maybe just from the motivation section.
Yeah, all right. So I'll start again with why I created this library. And so initially I made this for fun. I didn't have any intentions going forward with it. And I used to post, new creations and, new simulations on the developer forum. And so many developers used to give me feedback on my creations, which made me ultimately release this library on GitHub and then on the dev forum. And so one key reason why I made this was because there was no inbuilt physics engine, which was meant for two-dimensional elements in Studio from the start. and developers were not being able to create what they wanted to, and so I went ahead to create something that they could use possibly to create 2D games. And so this is actually inspired by a few other physics engines that run in the browser. For example, there's one by the name Matter.js, and there's more like Box2D and Toxic Libs. And so here's some simulations and basically sort of a gist of what you can do with this. And so you can see here's a wrecking ball that's knocking off a few boxes. And so there's a lot more that's going on here. And so there's also one that I created a few weeks ago, and this actually got a lot of reactions from people. And this was one that this is basically my favorite one out of all of these. And so there's basically a robot picking up these boxes and then putting them in a container. And so you can create basically anything you want, almost anything you want, because it's not with all the features that there should be. So there's no vel constraints, or you can't connect two objects together properly, basically. And so now I'll be going through, what all objects and what all physics objects exist in the library. And so the key physics objects are points. This is basically the base of every other physics object that exists. And if these didn't exist, nothing would basically exist. And so then comes constraints. So these are basically used to connect 2 points together. And so there are 3 types of constraints. First one is the verb constraint, then comes the spring constraint, and then the rod constraints. And then comes the rigid bodies, which are basically structures of constraints. So basically, if you want to create a rigid body that's in a shape of a square, you end up connecting 4 constraints together. And so the core of the library, which handles all of the rigid bodies, the collisions, the constraints, the points, that is basically what the engine is. And so each frame, so every time render step fires, it basically updates the positions of all rigid bodies. It then detects the collisions, and if any rigid bodies are in a collision, then it'll apply some force to separate them. So this is basically what collision response is, and then they'll update the positions again after applying the forces. Then I would render the rigid bodies on the screen. So change or fluctuate the positions of the UI elements on the screen, and then I would update any custom constraints that have been drawn on the screen, and then just render them. And so I follow a structural hierarchy. Yeah.
Could I ask a question?
Yeah, sure.
You're explaining at the top that the points were fundamental and everything needs to be.
Yeah.
I'm not sure what you mean by base. Like, would a square have 4 points, or like what?
Yeah, so a square would have 4 points and a constraint would have 2. So you're connecting 4 points, basically the corners of the square, with these constraints. And so every other physics object is being made possible by the points. If points didn't exist, constraints or rigid bodies won't exist.
Okay, yeah, I see what you mean.
Yeah, and so I follow a structural hierarchy in this library. And so at the top is the engine, which controls basically everything that goes on. And then comes the rigid bodies, the constraints, and points. And so you know what the rigid bodies are. These 2 constraints that are being, that are parented to this engine are actually custom constraints and points. So how these are different from the constraints and points in the rigid bodies, that let's say you want to connect 2 rigid bodies together, say with a rope or a spring, or you want to connect a point with a rigid body. So that's where these 2 constraints, these constraints and points will come into handy. And so the constraints inside the rigid bodies are basically the edges, and so the points are the corners of the rigid body, as I explained earlier. And so now we'll look into how different physics objects function. And so how I calculate, how I solve constraints, and how our rigid bodies function, basically that. And so points are essentially vectors on the screen. So they're just a dot on the screen, which have a reference to the position on the screen. And so this vector is changed over time. And so each time the render step is fired, they're changed according to the forces being applied to it. For example, gravity, or maybe friction, or any other force that has been initialized by the user. So let's say you want to apply a force towards, let's say the right side of the screen. So basically, all those forces make this point move. And so each frame, I calculate the point's velocity, I add the forces to it, and then if the point is parented to a rigid body, so if it's a part of the rigid body, I divide the force by the mass of the rigid body. And so now I apply the friction. And so if the point is touching the edge of the screen, or if it's touching any other rigid body, I'm applying the friction dampening value, and if it's not doing any of those, I'm applying the air friction value. So basically, it's suspended in the air. That's when I apply the air friction. And so then I limit the velocity if it crosses the max velocity. So you can specify different bounds to how high or how low a velocity can be. So this basically constrains the speed of the point. And then I just add the velocity to the point's position, which makes it move. And so there are three types of constraints, as I told you. There's this rope constraints, the spring constraints, and the rod constraints. And so for rope constraints, how they function is that you can basically you can bring 2 points really close to each other, but not any closer, and you can't basically have the points go too far from each other. So there's a lower limit and a upper limit to how far or how close the points can come. And so when solving rope constraints, I just check if 2 points are really close to each other. So let's say they're 2 pixels apart. Then I'll have to separate them so that they don't just go into nothingness, or they just don't, be basically a dot on the screen like any other point. Or if they're too far from each other, let's say they're exceeding the limit of going far from 100 pixels, then I have to constrain it back to 100 pixels. Basically, that's what row constraints are. And so to calculate the force that I need to apply to both the points, I first need to calculate an offset percentage. So how far or how close are the points to each other? And so what this rest length is, basically you can see, calculate the offset percentage between the rest length and the current distance between the points. And so what this rest length is let's say the uniform distance that has to be maintained on the upper limit or the lower limit. So let's say you want to have a distance between the points not more than 100 pixels, then the rest length is 100. And so I can easily calculate the offset percentage, so how far or how close the current distance is to the rest length. And so I can do that by subtracting the current distance by rest length and then dividing it by the initial value. And so then I can calculate the force to apply to each point. And so half the force that I'm calculating is applied to each point in opposite directions. So I'm subtracting one force from the position of this point, and then I'm adding this force to the position of the other point. And so I can calculate the force by just subtracting the position of both points, multiplying it by the offset percentage that we calculated earlier, and just dividing by 2. So half the force is applied to both points. And so for rod constraints, they're basically the same thing, but we want to have a uniform distance. Yeah, you want to say?
Question about the rope constraints?
Yeah, sure.
So firstly, I was curious why they're prevented from being too close. Like I would think of a rope as just constrained too
basically
far.
a rope, basically you want to have a rope constraint. So basically they're like the 3D rope constraints that you have in Roblox. And so you can have let's say 2 rigid bodies are connected with a rope constraint. So you can have both rigid bodies come close to each other and be less than the rest length that we want them to be. But if they exceed that rest length, we want to constrain them and so keep a uniform distance between them. And so this was actually brought by Boat Bomber on Twitter, and he, told me how if they come too close to each other, they're actually gonna, end up being nothing on the screen. So they're just gonna be a dot because both the points of the constraints are too close to each other. So there's nothing to see. And so we want to have a certain lower limit for the road constraints. So I normally take that as the thickness of the constraint. So let's say if the constraint is 3 pixels thick, that means the lower limit of the road constraint is basically 3 pixels. And so both points can't come as closer than 3 pixels apart. So that's why there's a lower limit on the road constraints. While there isn't any lower limit in the road constraints, there has to be a fixed constant distance being maintained between both the points. So in real life, you can bend rods, but you can't, make them smaller. You can't make them larger. So that's why there has to be a constant distance between both the points for road constraints. And so we just need to calculate the force the same way we do for road constraints. But here we're just checking if, the current distance between both the points is less than or greater than the reverse length we want it to have, basically. And for spring constraints, it's the same scenario as the rope constraints. We're just checking if the distance between the 2 points is not equal to the uniform distance that we want to have. And then we just apply Hooke's law to give it a springy behavior. So, it's wobbling around, it's moving around like a spring. And to do that, we just need to use Hooke's law that is minus kx, where x is the displacement and k is the spring constant. And so we just need to multiply the unit vector between the distances of the point. So the position of the point, we just subtract them, find the unit vector of that, and then we multiply it by the spring constant, then, multiplied by -1. And then to find the displacement, we just need to, subtract the current distance from the rest length. And so that's how you can find the spring force. And so this is how I calculate each constraint. And so now for the rigid bodies. Rigid bodies, as I told you, is a collection of constraints. And keep in mind, these are rod constraints because we want to have the edges of the rigid body intact at all times. And so these constraints are basically connected to each other. And so there are two types of, yeah, sure. You want to speak something? Oh, okay. So, yeah. No, you can say whatever you're saying.
I didn't say anything, sorry.
Oh, or sure, okay. So there are two types of rigid bodies. One is the default rigid bodies, and one is the custom one. And so there's just one difference between both of these types, so there's not much difference. And the difference between both is that the default rigid bodies require a UI element for a reference. So it can be a frame or a text label or an image label. And so how this is a reference is that we're taking its 4 corners, creating 4 points on the corners, and then connecting these 4 points with the constraints, rod constraints. And these can only be rectangles or squares because that's how the GUI objects and the UI elements of Roblox are. They can't be, a circle perhaps. Their hitbox remains a square or a rectangle. And for custom rigid bodies, they do not require a UI element for reference. So you can specify your own constraint structure, so how many constraints you want, or where these constraints are placed, or where the points are placed. And so this can be used to create triangles or any other shape, polygon, other than squares or rectangles. And so this is pretty good if you want to have, let's say, collisions between different types of polygons and not just squares and rectangles. And so, yeah.
Actually, keep going. Sorry.
All right. Yeah. So both types of rigid bodies function the same way. So the only difference is how they're created and not how they function. And so for rigid bodies, each point and the constraint of the rigid bodies is updated. And so by updated, I mean all the forces are calculated, the point is moved on the screen, the constraints are constraining the points. That's what I mean by updated. And then I detect the collisions between two rigid bodies, and I loop through each rigid body, and then I loop through other rigid bodies to check if there's any collision between them. And so if there is any collision, then forces to the points and constraints are subsequently applied to both rigid bodies that are colliding so that they're no longer colliding and they're separated from each other. And then I'm rendering the rigid bodies on screen. Now, here's another difference between custom rigid bodies and default rigid bodies is that the base UI element of the rigid body, default rigid body that we use as a reference, this UI element is visible, but the other constraints or the edges that we made aren't visible. And so the UI element is updated by changing its position and rotation according to the point and constraint structure and how the points and constraints are moving on the screen. Whereas in custom rigid bodies, they're basically hollow. There is no reference UI element. So we have to render the constraints, the edges of the rigid bodies in order to show that this rigid body is here, this one is here. And so these lines are rendered on the screen. And so that's the difference between default and custom rigid bodies when they're being rendered. And so now this segment is really important and one of
I have
my
a question about
favorites.
that.
Yeah, sure.
Have you considered triangulating the rigid bodies so that you can fill them in with triangles?
Yeah, I mean, I haven't done that because that is performance heavy, and considering how many calculations are being made, I don't think it is, it should be a feature, but you can always go ahead and create your own triangulation algorithm and just go fill the rigid bodies according to what their positions are. And so this isn't an inbuilt feature, but you can surely make something on your own that can fill the rigid bodies.
Okay,
And
and then
so,
related to that,
yeah. Yeah, sure.
So I was thinking that that's kind of what you were doing. Like,
Yeah.
well, I was wondering, how are you calculating the mass?
You can specify the mass, and by default the mass is 1 for all the rigid bodies.
Okay, I see.
Yeah. And so for collision detection and response, this is one of my favorites because of how complex but rather easy it is. And so each frame collisions are detected for each rigid body, and if two rigid bodies are deemed to be colliding with each other, we handle this collision by applying certain forces to both rigid bodies so that they're separated and no longer colliding. And to detect collisions or to say if two rigid or to determine if two rigid bodies are colliding, I use the separating axis theorem. And what this theorem states is that as long as we are able to draw a line, also known as an axis between two objects or two polygons, they do not collide. And so if there is no possible line separating both rigid bodies, we're basically saying that the rigid bodies are colliding. And so how I'm applying the separating axis theorem is that we first loop through each rigid body, then we draw an axis parallel to this edge. So let me just come over to the code. So if we just go in the rigid body file and scroll down a bit, so over here, you'll see that we are looping through all the edges of both rigid bodies. And so this is quite a fancy way of, looping through two arrays in this one loop. And so what's happening here is that we're looping through each edge, and then we're finding an axis right just parallel to this edge. And then we're projecting both the bodies onto this axis. And what I mean by projecting the rigid bodies on this axis is that if you see this image over here, you'll see how the constraints towards the left, the farmost left and the farmost right, are basically projected onto this axis. And this is done by taking out the minimum and maximum dot products of all the positions of each rigid body. And so this is how we can calculate a minimum dot product of both the rigid bodies and a maximum dot product of both bodies. And I call this min A and max A and min B and max B. And then so with this information, we can actually say if this axis separates both rigid bodies. And that is done by first of all seeing if min A, so basically the far left point of the first rigid body is less than the farther right of the second rigid body, if that makes sense. So basically, min A is less than max B, and the same way min B is less than max A. And so we can say that these projections are intersecting. And if they do intersect, that means you can continue checking if there is any axis that separates them. But if they do not intersect, then we have basically found an axis that separates them, and so that means that both the rigid bodies don't actually collide. And so then we want to find two important pieces of information, and that is which vertex of the first rigid body is colliding with which edge of the second rigid body. And so there's a collision between a corner of the rigid body and an edge of the other basically. And so we want to find the closest vertex to the edge we just checked for. And
Right.
so
I just have a question
yeah, sure.
regarding the actual collision algorithm. So this is a diagram saying,
Yeah.
given an axis, you can determine by iterating over the edges whether this axis separates them.
Yeah.
How are you choosing like the axes?
Oh, so it's basically just on the line of the edge. So basically it's an axis. Just let's say there's not much difference in the distance between the edge. I mean the position of the edge and the axis. So they're basically just on each other, and so it's also parallel to each edge. And so basically, if the axis is passing through one rigid body, and wait a second, let me just show you the code real quick. And so I'm calculating the axes by subtracting the y and the x coordinates of each point on the screen. And so we're subtracting.
So you're using each edge as a potential axis
Yeah.
that separates.
Yeah.
So there's a theorem that says that if there's
As
a
long
separating
as-
axis,
yeah.
then one of these edges will be a separating axis.
Yeah, so basically separating axis, that's where it gets the name from. So if there's an axis separating two objects, then they're not colliding. And if there isn't any axis, that means they do collide, basically.
But it's not only that theorem, it's also that, like, yeah, there exists a separating axis, but also it's present as one of the edges of one of the
Yeah.
shapes.
Yeah, exactly.
Is there also any like assumption like these have to be like convex shapes?
Yeah,
Like
they
maybe
do have to be convex. So for concave shapes, this collision algorithm won't actually work, and so end up taking the projections as convex rather than concave. And so this is where this algorithm is faulty, and it just isn't made for concave shapes. Yeah. Yeah.
But could you just break up the shape into smaller?
Yeah, you can do that. Yeah.
Okay, cool. Thanks.
Yeah, and so we find the closest vertex to this edge we just checked for, and so we can say that this edge is has either pierced through the edge or is just touching the edge in a particular frame. And so with the above steps, we can actually calculate the depth of this collision. And so to calculate the penetration, we just need to subtract, we just need to perform a simple this thing. So to calculate, first of all, we need to see if min A is less than min B. And if that is the case, then we can subtract max A from min B. So, you can find this guy. You can subtract min B from max A to find this little, how far min B is from max A. And so the same way you can do it for max B and min A. So if the first rigid body is towards the left of this rigid body, we'll end up saying max B minus min A to find the penetration depth. And this is a scalar, by the way. And so next is the collision response. And so using the information that we found out earlier by detecting collisions, which is the collision vertex, which corner of the rigid body is colliding with the collision edge. So which edge is the vertex colliding with, as well as the axes that we checked for, and then the collision depth. So this is a scalar. And so using this collision depth and the axes, we can actually find a vector, which is, let's say, a collision vector or a penetration vector. And by multiplying the depth by the axes, we can find this vector. And we'll actually use this collision vector to find the force to apply on both the rigid bodies later on. And so for this, I'll actually take you to the engine file. Right, so here we are. And so we calculate the penetration vector, and then we calculate a t percentage value. And so what this t percentage value is that where is the collision vertex located on the collision edge? So let's say if a collision edge is straight, and so if the collision vertex, if this t value is 0.5, then we can say that the collision vertex is halfway the line. So you can sort of imagine how that looks, right? And so this is what this t value is. And then we calculate a lambda function, which I don't know what the derivation of this function is. I myself found this on MathStack Exchange, so I'll have to catch up with what this is. And so basically what this does is tells us another percentage value for how much we should, let's say that the collision vertex has gone past this collision edge, but we still want to separate both the rigid bodies. And so we want to have a alpha value, basically a percentage value, for how much we should move this collision vertex so that it's either lying on the collision edge or it's really close to the collision edge. So we want to, first of all, position both rigid bodies so they're separated from each other and then apply the forces. And so this is what this alpha value is. And then we calculate the ratio between the masses of each rigid body. And so say if the first rigid body has a mass of 10 and the other rigid body has a mass of 5, so the ratio is 2:1. And so the value of R1 will be 0.6666 and so on. And the value of R2, ratio 2, will be 0.333 and so on. And so now we just need to calculate a force and apply the force to this collision edge and collision vertex in opposite directions so that they're no longer colliding. And yeah, and so to do that, we just, multiply the penetration vector or the collision vector by all our alpha values, all our ratios. So 1 minus t is for, where this collision vertex lies on the line in terms of how far ahead it is from point 1 in the range of 0.1 and 0.2. And so if it's closer to 0.1, then more force is supposed to be applied to 0.1 than 0.2, so that it's sort of realistic to see if the point is colliding close to the corner of another constraint. The first point is supposed to move, with a greater force, so that, it's tilted towards the left, let's say, for example. And so a greater force is applied to point 1 if 1 minus t is greater than t itself. And so we multiply it by the factor, so how much should the point move out of the, basically, out, so that it's touching either collision vertex or it's close to the collision vertex. And then we multiply it by the ratio of the mass of the first rigid body. And this is done for both the points of the constraints. And then we just need to add this force to the collision vertex, which is just penetration into ratio 2, which is the mass of the second rigid body to which the vertex belongs to. And both these forces are applied in opposite directions. So from one, you're subtracting the force, and to the other, we are adding the force. That's basically what's happening. And so if you have any questions, we can take that at the end, just 2 minutes more because we're running out of time. And so this is the last thing that I'm going to show. And this is a code example, basically, for a rigid body suspended from a spring constraint. So you can see in this GIF below how this springy structure is moving this rigid body here and there, basically. And to do that, it's quite simple. It doesn't take much time. You just want to require the library, and then you want to initialize the engine by feeding it some screen UI instance to which all the UI elements belong to and will be parented to. And then you just need to specify some configurations like what's going to be the air friction or the gravity or any other physical property. And then in order to render constraints, which are, as I talked above or earlier, that there are custom constraints and there are constraints inside other rigid bodies. And so to render custom constraints, you want to create a canvas. And this canvas is basically just a confined area where all these rigid bodies stay and they can't go past that. And so then you just want to create a point from which this rope is going to be suspended. And then you just want to create a rigid body and then just connect both the rigid body and the anchor point with the spring. And so this is how you create the spring constraint. To specify type, then put the points of the constraints, and then you just need to run engine start, which is going to give you this simulation. And so that is it for my presentation. And so if you have any questions, feel free to ask. I'll be able to answer all of them. Yeah.
Thank you
so
very much. That was really
yeah,
interesting. We did have a scheduled event from 2:30, but it's not running this week, so we do have
yeah,
until 3 o'clock, and then there's a tea break at 3 o'clock anyway.
yeah,
So, yeah, we do have time for questions if
yeah.
anyone has any.
So does anyone have any questions?
How did you do the robot arm that moves the boxes?
Oh, yeah, let me just show that again. And so, just a second. Yeah, so here's the robot arm. And so this robot right here, I think I have explained it in a session we had in private. And so what I did was this robot has a target. And basically this is running using a genetic algorithm, which I trained. And so what's happening is that basically there's a target vector to which this robot is basically seeking for. And so this robot actually is rotating like that using inverse kinematics. And so what's happening is this works for only this particular, this particular situation. So if the boxes are towards the left of the robot and the container is towards the right of the robot. And so what it's doing is that if the robot does not have a box in hand, it's supposed to go pick some boxes up from the left side of the screen, so the left side of the robot, and the target is basically moved by a certain vector so that this robot reaches close to the box, and then it picks the closest box to the target. And then if there is a box attached to the robot, then the robot is supposed to move towards the container. And so another vector is applied so that the target moves towards the right of the screen. And so if it reaches above the container, we're supposed to detach this box from this robotic arm. And this cycle continues until all the boxes are, they're inside the container, basically.
It seems like you're explaining the
Yeah, the
simplest
AI
part
component.
going on.
Yeah.
Like,
I mean, the physics part of it is quite simple. There's just a stack of boxes, and then the white container in the platform is actually an anchored rigid body. So that's where all these boxes are kept in a stack. And so this is basically what's happening. It's not much to do with,
right.
the physical element. Yeah. So
Maybe I could say I could imagine a lot of different uh ways you could bend the joints of that
yeah,
arm in order to
yeah.
move from A to B. And it seems to be doing it seems surprisingly organic the way it bends and
Yeah, that's because of how beautiful inverse kinematics is. Yeah.
right, but so that still leaves the question of like there's a lot of different paths it can take. Which path does it take, and what principle is making it behave the way it is? as opposed
Yeah,
to like
so inverse kinematics is basically an inverse of forward kinematics, and so in forward kinematics, all the points are supposed to follow a target, while in this one, they're actually supposed to do the inverse. So that, let's say, for example, we're turning towards the right, and then we're immediately turning towards the left. And so you actually see a curvature that's formed towards the right and not the left. And so, if you know what I mean, or if that makes sense.
like what are you specifying to the arm? Like, are you telling it a
Just a
path?
target. Yeah, I mean, the head of this robot, basically the topmost point is actually following the target, and all the other points that are, in the robot, they're following each point, so each point ahead them, so they're following each point, just like that. And so the
Is that
topmost point is following the target.
So is it just solving like the sort of simplest,
Yeah,
the shortest amount of movement it can make in order to move
yeah,
like in the direction of where the target is?
yeah, sure. Yeah, basically that.
Cool. It's still like rather surprising how like intricate
Yeah.
and organic looking the like end result is.
Yep. It is pretty surprising. I mean, I trained it it was really sloppy, so at times the target would actually go too far, or it would go to, under this platform, and because of which, it used to fail and not pick up all the boxes. And how I handled the score system is how many boxes it's putting inside the container. And so if it, touch it in, if it, and later on, it will actually do this quite often, that it will go under the platform or quite a bit over the platform. And to prevent that, I used to, kill this and, basically start a new generation each time it did that. And so basically that.
Wait, so are you saying you said you trained it? Are you doing reinforcement learning or something?
Can you repeat, please?
I thought you were I thought this was like a basic algorithm where you just chose a box, but you said you trained it, so are you
Yeah.
involving kind
I
of
mean, I just waited for it to be exactly perfect or close to perfect, and so this genetic algorithm keep running until there were like 160 generations or so where it finally, started to perform well. And so it took a lot of time to train this, or essentially wait for it to work and train itself.
Oh, so because when you said target before, like
Yeah,
I
so
thought
the
you
target is the vector which this robotic arm is following, and so this target is incremented with some force or some, vector which makes this target move from left to right or right to left. Basically, this is what the robotic arm is following.
right, but I don't understand. Is it asking inverse kinematics what to do in order to move closer to that point, or is it involving some learning
According
process?
to, if there is a box attached to this point, box attached to this robotic arm, and so if there isn't any box attached to it, you want to go towards the left of the screen or the left of the robot to pick up a box. But if there is a box attached to the robotic arm, then you want to go towards the right of the screen to drop the box, and the cycle just repeats.
Right, but where's the learning process in this? Like, does something
So
different happen if you
this is
run it
basically
2 times?
reinforced learning. And so if there are any red flags, it's gonna learn not to go there. And so not to do, not to continue doing that red flag. As an example that I told, that if the target goes too far from all the boxes, if there is no box attached, you don't want to do it. You want to restart a generation or start a new generation and, do the same process until the target actually goes closest to the radius in which I'm accepting it to, the radius in which all the boxes are. And so if the target is inside the radius, you want to go directly to the closest box that exists in that radius.
Hey, maybe I'm misunderstanding, but what's the what decision does it have to make? Are you programming it to like go towards the closest target, or is there some point at
Yeah,
which
I am programming it to go towards the target.
right? So what decision does it need to make? Like if you're like doing reinforcement learning, like my
Yeah,
understanding is
so
that it
it's
has
just want
some
to
decisions
reach
to
for the target or the container depending upon if it has a box or not. This is what the reinforcement learning is handling. And the rest, like picking up the boxes, I'm basically attaching the box myself and not the robot picking up that box basically.
Okay.
Yeah. So if you want me to explain it better, I can do it someday. I can share the code basically, or somewhat share the code, and so yeah, you can see by that.
Okay, that'd be interesting. Sorry, I
Yeah.
think I like cut off Ethan a few times in my questions. Did you have
Oh yeah.
anything more to add, Ethan?
No, it's fine.
I
Yeah,
forgot
sure.
what they were.
Okay. Um, I did have another question. I'm sort of
Yeah,
I have no familiarity with physics engines, and
yeah,
I imagine this is like a incorrect thing to do, and I'm curious like what goes wrong. Say with the rope constraint, you want to prevent like these 2 points from being too far apart. Like what happens if you just like when they become too far apart, you just like set the position back to like so that they're like close enough together,
I
like
mean
as opposed
that's
to like
that's what's happening. So basically half the force applied to it is actually immediately bringing 2 points closest to each other. I mean, as far as they can come. So basically the forces are bringing both the points to the specified rest length. So the distance between the points is reduced in one go, basically.
oh, so that force doesn't get applied across like
Yeah. So
multiple
it's not a
frames.
unit vector, it's actually a force. Basically, the difference, I mean, how much I should increment it so that it immediately, maintains a rest length between, so I mean, a length equal to the rest length, basically.
Uh-huh. Okay.
Yeah. All right. So any more questions?
Thing I was thinking about for the custom rigid bodies is like, so
Yeah.
you're applying forces based on each individual point. I was wondering like if you could sort of aggregate that and just apply it all to the one assembly of
Yeah, but
points.
that'll actually make, I mean, yeah, you can do it, but to apply an aggregate, I mean, it is what's happening, and so somewhat the same forces are being applied to each of the point of the rigid body, but that may actually end up giving an unnatural, sort of movement of the rigid body. So let's say if you're applying a force to the right, and if all of the points of the rigid bodies are gonna have that force, it's actually just gonna move, in an unnatural way, the rigid body. And so you wanna sort of have different forces for each point. But the constraints
Okay.
will end up doing that job for you and keep both, even the slower points, together.
Okay.
Yeah. And so any more questions?
Those notes you've put together, is there any way you could make those available? Or are they already somewhere?
Um, can you repeat?
The notes you were just presenting, is there any
Yeah,
way
sure. I'll share them. Yeah.
that'd be excellent?
Yeah, all right. So I guess we don't have more questions, and so that is it for this session. We went really overboard with the time. We're 20 minutes ahead. I mean, we exceeded it by 20 minutes, so I guess we should end it all here. And so if you have any more questions, you can ask me in the text channels. And so, yeah, I guess that's it. And I'll see you next time. Yeah.
Thank you,
Thank you
Jeff.
very much, Jai. Really appreciate
Yeah, no problem. Thank you for attending.
Thank
Yeah.
you.